I'm going to redo yesterday's video because it turned out quite terrible. But I'm looking at section 8.3 and 8.2, but there were no questions asked about 8.2. So we're going to jump straight into 8.3. So apologize if you watched the last video. The last video was terrible. I tried to live stream it on YouTube, and my 40-minute video got cut down to 8 minutes of material that actually streamed because of internet connectivity. So let's take a look at a couple of these things. I'm just going to do the whole video over, so if you've seen some of it, you may want to skip around. But we're going to start with number 1. So number 1 asks to graph some sets of complex numbers. So I'll do a couple of these. We'll take a look at these. Set A was the set of complex numbers denoted by Z. Given that, and this long straight line, which is usually larger, goes above and below the regular text line, is the condition line. So everything after that is a condition. The condition is 1 is less than or equal to the magnitude of the z's, or the distance of the z's is greater than 1, but at the same time, the distance also has to be less than or equal to 4. Right? And so we think about what's happening here. We don't actually have to do any algebra or math. In an axis, I have an x as the regular x, the horizontal. My y is the vertical. Right? The x is also typically called the real part of the number, and the y is the imaginary part of the number. So I have this, and for the magnitude of this thing to be between 1 and 4, that means for the magnitude to be greater than 1, there's a circle at 1 that it has to be outside. For the magnitude to be greater than 1, it means it has to be further than 1 away, so it's outside a unit circle of radius 1. But for it to be less than or equal to 4, that means I have another circle at 4, but it has to be inside. It has to be less than that or equal to that. And because it's less than or equal to, it's a solid line. For my smaller circle, because it was greater than or equal to, it's a solid line. And so it's all of the numbers in between those two circles, which is called an annulus. That's A-N-N-U-L-U-S. Or you can call it a donut. It doesn't matter. But it's all of these values. So that's what set A looks like. I'm going to erase this, so if you want to pause, if you need to pause to write down what I've got here, go ahead and do that now. But let's take a look at another one in that same number 1. We'll do one more, and then I'll leave the rest to you. Let's look at B. Set B is the set of all z values. And we're going to rewrite these z values as x plus iy. Because the condition is on x and y, that condition is that x has to be less than y. That is to say that the real portion of the imaginary number has to be less than the imaginary portion of the complex number. And so for us to look at this again, I've got the x, which is my real portion, my y, which is my imaginary portion, right? But I can still treat them by x and y's if I refer to my number as x plus iy. And so this condition, x is less than y, is the same thing as y is greater than x, right? And this is just a line. If I look at the line on the equality, y is equal to x, that's just a straight line. It goes to the origin that has a slope of 1. I'm going to do it dotted because the condition is a strict inequality. Y is greater than x. And for y to be greater than x, that's all of those values up top. And so it's a dotted line, but with everything above that dotted line. You can use similar tactics to look at C and D. They're not terribly difficult. I think this one probably may have been the most difficult, but that's A and B. You can look at C and D. Hopefully you can get through those. The next one I had a question on was number 3. So I have 8.3, number 3. And that says to write the number root 3 plus I in polar form. Sometimes instead of polar form, you'll see this written as trigonometric form. Because for a complex number, when we write it in polar form, we're going to use trigonometric expressions to do so. So in order to do this, the first thing I want to do is figure out what my radius is, my r. And the r is just the Pythagorean distance. So it's the square root of the x value, which is the square root of 3, squared, plus the y value, which if you just have an I, your y value is 1. Because if there's no number in front of it, it's just like it's a 1. And so I have r is the square root of the square root of 3 squared plus 1 squared. Simplify this. The square root of 3 squared is just 3. 1 squared is just 1. And so the root of 3 plus 1 is the root of 4, and that's 2. Okay. The next thing I want to find is theta. And theta is just tan inverse of the y value, which is 1, divided by the x value, which is the square root of 3. If you rationalize inside there, that denominator, this becomes the tan inverse of root 3 over 3. And you should recognize that as pi over 6. So there I have it. I have a radius is 2. I have my theta, which is pi over 6. And therefore, the answer in the end is written as r, so 2. And then a parentheses, and then the cosine of that angle plus I sine of that angle. So that gives me cosine of pi 6 plus I times sine of pi 6. There we are. Okay. I also had number 16. Questions on 16. It looks like it says to take a complex number and cube it. That number is 2 square roots of 3 minus 2i all cubed. Well, the first thing that I want to do is take this complex number and rewrite it in trigonometric form or polar form. And to do that, again, I find my r. So r is the square root of 2 roots of 3 all gets squared, plus negative 2 gets squared. So if I simplify this, 2 roots of 3 squared, that's 2 times 2 times another 3, so I get 12. Negative 2 squared is 4, so I have the square root of 16, which is 4. So I have my radius is 4. Theta is again the tan inverse of the y value divided by the x value. And then of course, because tan inverse has an output in quadrants 1 or 4, you'll need to make sure that you don't need to adjust your answer. If my answer should be in quadrant 2 or 3, say if I had a negative x value here and a negative y value, that would put me in quadrant 3. I'd have to add 180 degrees to my tan inverse. I don't have to do that because a positive x value and a negative y value puts me into quadrant 4, so my tan inverse will give me a value in quadrant 4. Right? So I've got tan inverse of negative 2 is the y value, divided by 2 root 3. If I simplify, my 2's cancel out, so this gives me the tan inverse of just negative 1 over root 3. But that's the same thing as the tan inverse of negative root 3 over 3 if we're to rationalize that denominator. Right? And that's negative pi over 6. So I need the board space, so I'm going to erase this, but I'm going to note that my r is 4 and my theta is negative pi over 6. Maybe I'll write it up here in the corner. So if you need to write this down, pause it now, because here it goes. Okay. So I have my r, I have my theta. That means I can rewrite this number as r times the cosine of theta, so cosine of negative pi over 6, plus I sine of negative pi over 6. And this whole thing now is raised to the third power, so I'm going to put another big bracket out here because the whole number gets raised to the third power. And then the theorem says that when I have some trigonometric form of some number raised to a power, I take the radius to that power. So this is to say that I have 4 to the third power times, and then my angles simply get, in this case, tripled because my exponent is 3. So I have cosine of 3 times negative pi over 6 plus I times the sine of the same angle, 3 multiplied by negative pi over 6. 4 to the third is, well, 4 times 4 is 16, times that last 4 gives me 64. If I simplify inside the angle here, 3 simplifies with 6, leaving with a 2 in the denominator. So I have cosine of negative pi halves. Okay. Plus I times the same, it'll end up being the same because it's 3 times negative pi over 6 as well. I can simplify because cosine of negative pi over 2 is 0. But sine of negative pi over 2 is negative 1. So I have I times negative 1. The 0, excuse me, the 0 doesn't matter, but 64 times negative 1 is negative 64 times that I. So I have negative 64I. And that'll be my final solution here. Okay. And then I had questions on both number 20 and 21. They're very similar, so I'm going to do number 20 and I'll leave 21 to you. And if enough people can't get through it, then post it on the discussions, see if somebody can throw an answer up there. But if you can do 20 and then can't do 21, let me know and we can do it on the next video for Wednesday, tomorrow's class. But let's take a look at number 20. It says, find the fifth roots of I. So that is to say that I want to take I to the 1/5 power, right? But I want to find I in terms of polar coordinates or trigonometric form. So I itself, let me do this in perhaps blue. I is the same thing as 0 plus 1I, right? And so if I want to find the r associated with I, that would be 0 squared plus 1 squared. But that, of course, is, well, 0 squared is still 0, 1 squared is still 1, so that's just a 1 under the square root. And the square root of 1 is 1. So I have that, and I've got my r as 1. And then, of course, if I try to find theta, theta is the tan inverse of 1 over 0. And I have issues here because I have the tan inverse of an undetermined number. Right? So if I think about what's happening here is on this axis, I is just right up here on the imaginary axis. And so it should be pretty obvious that my angle is 90 degrees, right? And the reason that I get some undetermined number here is that the graph of tangent has asymptotes at negative pi halves and positive pi halves, right? It looks like that. This happens to be on that pi halves, that 90 degrees where we get that asymptote. So I don't actually have to do the tan inverse. In fact, I can't because it's the tan inverse of undetermined. But if I get that, it tells me that I'm either on pi halves or negative pi halves or some multiple of them. And so I can rewrite I in trigonometric form as a radius of 1 cosine of pi halves plus I sine of pi halves. And then all of this now is to the 1/5 power. So I'm going to get 5 answers out of this. The first one's going to start at Z0. My index is 0 because I'm going to add nothing to the angle that I get. The next one will be Z1 because I'm going to add 1 multiple of something. And then the next one's Z2 because I'll add 2 multiples of something, and we'll talk about that when we get to it. But Z0 is my first solution here. I'm going to take the radius that I have in my trigonometric form to the 1/5 power. And then I get this cosine of pi halves. And I think the answer wants it in degrees, so I'm going to switch to degrees. Instead of writing pi halves, sorry if you're writing this down, more sorry if you're writing it in pen, I'm going to write this as 90 degrees. And so in my Z0, my angle for my cosine and my sine is that 90 degrees. And it's the 5th root, so it gets divided by 5. If it were the 6th root, it would be divided by 6, and so on. And so then 90 divided by 5 is 18. And so my angles are 18 degrees. This radius is 1 to the 1/5, but that's still just 1. So I get 1 multiplied by the cosine of 18 degrees plus the I times the sine of 18 degrees. And that's my first number. I don't want to change it back into anything. This is how this, I believe, is how the answer wants it. Your radius is 1, your degree is 18. You have to just put in the radius and then the degree in both places. To figure out Z1, the next one is similar formula. Z1 is that same radius, 1 to the 1/5, but I'm just going to write them as 1 because they're all going to be 1 at this point. They're all going to have the same radius. And then I have the cosine of my original angle, which was 18 degrees, the original angle from Z0. But to this, I'm going to add a whole circle, 360, multiplied by 1. This index 1 matches the index of my Z. And so I have that, but it's all divided by 5. 360 times that 1 is divided by 5. And then I have my plus I times the sine of the same thing, 18 degrees, plus 360 times that 1 divided by 5. Well, 360 times 1 is 360. Divide that by 5, you get 72 degrees. So to 18 degrees, I'm adding 72. So then I end up with 1 multiplied by the cosine of 18 plus 72, that's 90 degrees. And of course, then my sine is the same number, so I get plus sine of 90 degrees. And that's Z1, my second solution. And every single one of these has the same formulation. In fact, I'm not going to erase the whole thing. I'm just going to erase this and call this Z2. If I'm trying to find Z2, I add 2 circles divided by 5. And so really I'm just adding another 72 onto the last angle because now I just have this number as double, right? So this should be 144. And so I end up with Z2 is 1 times the cosine of 18 plus 144, which is 162. And so I should have cosine of, what did I just say? 162 degrees plus I sine of 162. Which again, if you'll notice, let me just rewrite Z1 up here. Let me maybe just write them all. Z0 was 1 times the cosine of 18 degrees. Z1 was 1 times the cosine of 90 degrees. Z2 is 1 times the cosine of 162 plus I sine 162. If you just keep adding that 72 degrees, you'll get the next one. So Z3 is 1 times the cosine of 162. And if I add 72 to that, I have my next guy. So I have cosine of 234 plus I sine of 234. And I have one more, right? I should have 5 total because it's the 5th root. I have my 0th as my first, second, third, fourth. So I'm looking for one more. Write it over here. Z4 is then just 72 degrees more than this one. So if I add 72 to here, then this gives me 1 again times the cosine of 306. Plus, of course, the I sine of 306. I ran out of room on my super duper large erase board here. But that's all of them. I have from 0 to 4. And if I tried to add 72 to Z4 to get to the next one, I'd actually end up back at Z0 once you erase off that circle, right? So if I try to go Z5, if I'm just adding 72 to 306, right, the angle here would be 378. But that's going around a whole circle and 18 degrees more. So it's the same thing as Z0. That's why we can stop there, because we're just going to run through these guys as a cycle if we were to keep going. So that's it. That's my 5 solutions. You can formulate each one of them by adding, if I were looking for Z4 and none of the others, then I would just take that original 90 degrees divided by 5 and 4 full circles, then divided by 5 and add those together. But if you go from the beginning, you find the angle that you're adding between Z0 and Z1, you're going to add that same angle however many times until you get to your last complex number. So hopefully that helps. 8.3, number 21 is done similarly, but it's with a more, a little bit different number, a little uglier a little bit. So try it. Let me know if you get through it. You can subscribe to my channel if you want. That'll give you, I think, an email every time I post one of these things. But I'm going to email you through Canvas anyway, so maybe it's not necessary. But anyway, there we are. And I will post another video for 8.4 sometime in the middle of the day on Wednesday. So if you have questions about 8.4, go onto the discussion boards for 8.4. Talk about them amongst yourself. That's probably the best thing to do, is post it up on the discussion board, because if somebody else in class can answer it, then you're doing both of you a service in getting both of your discussion board quota met. And also, if you're teaching it to somebody else, that's also reinforcing your own learning. So, do that. And then, of course, I'll still be happy to do them on the board here as well. So, all right. Thank you.